So what are these orbitals like? The shapes of these orbitals come from very complex mathematical calculations. And there are 4 numbers, they're called quantum numbers, that specify the different shapes. We're going to talk mostly about just 2 of those. The principal quantum number, that specifies the principal shell of the orbital, the overall energy level. And so this is where thinking of the orbits, even though we know they're wrong, is convenient. The principal quantum number, 1, 2, 3, 4, 5, is similar to those orbits in the Bohr model. Whereas you go up in number, the energy increases in the distance, the average distance from the nucleus will increase as well. And then within those levels or shells, there are subshells. And this tells us the shape of the orbital. These have letter indications, S, P, D, and F. They come from historical descriptions of lines, and that's why they're not A, B, C, D. So just S, P, D, F. Sorry about that. It's just how it is. So this is a representation, a dot representation of a 1s orbital. So a region in 3-dimensional space, and this is like taking a multiple exposure of an electron. So like every second for 10 minutes, you take a picture, and the blue dot is where the electron is then, right then. And so it's moving around, but it's generally within this region. Could it be outside? It could be, but most likely it's within this region. It's more likely nearer the nucleus than farther away. But this is a region of probability. So the dot density represents the probability. The probability is greater here. So we can also represent this as a geometric shape. These are much easier to draw. It takes a long time to draw those little dots. So a sphere for the 1s orbital. What you have to be careful of is thinking that this is a container that contains the electron. That's not true. It is also not true to say that the electron is just moving around on the surface of this container. This is just an easier way of representing this probability map. So the sphere is representing the volume within which the electron would be found 90% of the time. 10% is going to be outside of that, but we're going to call 90% good enough. So if we superimpose both of those images, we see that sometimes the electrons are outside. Now, could it be over here? It could. Not real likely, very improbable, but it could. Most likely it's just going to be a little bit outside. Any questions? So an atom of hydrogen that we haven't messed with by zapping it with energy or anything, it's just sitting around, hanging around at room temperature. Its electron is going to be in the 1s orbital. That is the lowest energy place that an electron can be. It's called the ground state, or lowest energy state. Electrons generally seek out the lowest energy state, just like water seeks the lowest part of your yard. If something floods, the water goes to the lowest part, right? I have teenage sons. Teenage sons tend towards the lowest energy state, which often is laying flat in their bed, texting someone, right? They sleep a lot. Do they get up and do stuff? Do they get excited and go play football and things? Yes. But they always return to that low state, right? So that's what the electrons are doing. They'll go to a higher energy, but then they always come back down. Everything, just chill. So when it absorbs energy, it can go to a higher energy orbital, and that's called an excited state. Just like with the teenage boys, it's unstable. So atoms are going to have one ground state, where all of the electrons are in the lowest energy orbitals possible. But there are many different excited states. You could excite 1 electron, you could excite 5 electrons, they could go up 1 level, 2 levels, there's all sorts of possibilities. But there's one ground state. So this is the 1s. So The n equals 1 principal shell has one subshell, and it's the s. N equals 2, that second level of higher in energy, has two subshells. It has an s orbital, and it also has a p subshell. So this orbital is higher in energy and slightly bigger than the 1s orbital. And so far, this is not looking that much different than the Bohr model, except this is three-dimensional, and the Bohr model looks two-dimensional. But this is what the p subshell looks like. The p subshell has three different orbitals in it, and they are not spheres. So here's the dot representation and the geometrical shape. They kind of look like two balloons tied together or a dumbbell, and the three of them are oriented perpendicularly in space. So there's three of them, but they fall along the axes x, y, and z. They do not overlap with each other at all. Is it getting weird? Yeah, we're not done yet. So, shell 1 has one subshell, and that's called the s. It's an s orbital. Shell 2 has two subshells. Shell 3 has three subshells. Shell 4 has four subshells. So that's kind of convenient, right? The number of the shell tells us how many subshells or sublevels it has. Excuse me. For 2, it's S and P. 3, SP and D. 4 is SP, D, and F. So those four letters. Questions yet? Other than why? Yes.
What do you mean if they're on the same, they're around the same axis? What do you mean they don't overlap?
That's a good question. So how do these not overlap? Well, if you notice, right at the center, there's nothing. It's a little, this one's a little distorted. So there's one going this way, and one going that way, and one going up and down. And because they're narrower here and taper really to nothing, they actually don't overlap at all. It's like tying balloons together. Yeah, so there's these three different orbitals in that sub-level of the atom. I'm going to come to an analogy with a hotel and people sleeping in beds that hopefully will make a little more sense. We're going to go through the ugly real stuff first. So the third principal shell has three subshells, SP and D. So the S orbital is, the 3s orbital is going to look just like the 1s and the 2s. It's just going to be larger. And the 3p orbitals are going to have the same shapes as the 2p orbitals, but just slightly bigger and higher in energy. And then we have the D subshell, which has 5 orbitals. And those are their shapes. Now, we did not just think it would be cool to make these shapes. This comes from mathematical models approximating the energy characteristics of atoms. So we're not making this up, even though it looks a bit Dr. Seuss-ish. You definitely do not need to know the shapes of those 3D orbitals. I mostly show them to you to, I don't know, blow your mind or scare you, or I don't know, just so you've seen them. So these 4 aren't so bad. It's this one that's really weird. It's like a little kid going swimming with their floaty ring on. I don't know.
I have a question.
Mm-hmm.
And are those stationary or revolving?
That's a good question. Are they stationary or revolving? They're stationary. But given that the atom is basically a sphere and can rotate and tumble, in terms of things around it, they would be changing But in terms of like relative to the nucleus, they would be
But
stationary.
if they change, it would be in relation to the whole sphere.
The whole atom, yeah. They would all move together. Yeah. Good question. So we need a system of identifying where the electrons are in all of this mess. So an electron configuration shows where the electrons are, what orbitals are occupied, how many electrons are in there. So for hydrogen, it's relatively easy because there's only one electron. So that one electron in its ground state is going to be in the 1s orbital, the lowest energy shell, the only orbital that's there. And so 1 is the principal quantum number. The shell S tells us which subshell, and the superscript 1 tells us how many electrons are in there. This is an example where chemists do write the number 1. So there's 1 electron in the 1s orbital. We can also do this with diagrams. An orbital diagram, we draw boxes. So here is a box representing the 1s orbital, and the electrons are represented as arrows. Usually half-headed arrows, and the direction is important. They can be either up or down. We'll get to that. So for ground state hydrogen, it's going to look like this, a box with an arrow pointing up. In these orbital diagrams, the direction of the arrow represents electron spin. The spin is a fundamental property of an electron. Do you know what Beyblade tops are? Little spinning tops? Some of you do. Beyblades, they can either spin clockwise or counterclockwise. It depends on the launcher that you've got, right? So electrons are a little bit like that. They're going to be spinning in one direction or the other. So positive or negative, up or down arrows. Something called the Pauli exclusion principle says that orbitals can hold no more than 2 electrons with opposing spins. So if you have 2 electrons in the same orbital, one has to be spin up and one has to be spin down. And then they can be in the same space. You'll never see 2 that are both up or both down. I know this is not making much sense yet. Okay, let's try writing electron configurations and orbital diagrams for helium and lithium. I like the orbital diagrams first because they're more of a picture. So let's look at helium. How many electrons does helium have? 2 electrons. So we got 2 electrons, and so we're going to try to draw a picture of what's going on. So the lowest level is n equals 1. In n equals 1, there's 1 subshell. It's the s subshell. Each orbital can hold 2 electrons, but they have to be spin up and spin down. So here, 2 electrons, we can put 1 up and 1 down, and they can be together in that orbital. So that's the orbital diagram. And the electron configuration would be 1s2, because there are 2 electrons in this box labeled 1s. So that's the electron configuration. Let's look at lithium. How many electrons does lithium have? 3 electrons. So the lowest energy is what's going to fill up first. So the first shell contains 1 subshell, the s orbital, and that can hold 2 electrons. Where's the 3rd electron going to go? It has to go to the next shell. It has to go to the 2, shell 2. Well, shell 2 has 2 different subshells. It has the S and it has the P. And the P is, there's 3 of them. So that 3rd electron goes into the next shell. That's the orbital diagram. The electron configuration would be 1s2, 2s1. And you thought net ionic equations were confusing. Questions? Okay, there it is. So I'm going to keep going through the science part, and then I'll get to my crazy analogy. So in multi-electron atoms, things get messed up because of interaction between the electrons, and this is why the Bohr model doesn't work for anything but hydrogen, because the electrons interact with each other, and it kind of screws things up. So this is what happens. So here we have a diagram representing energy increasing here. So here's energy level 1, shell 1, 2, 3, 4, and 5. And as you go up in number, they increase in energy. Okay, so that makes sense, like going up the rungs of a ladder. So there's the first level only has one sub-level, one subshell. The second has 2. So there's 2s and there's 2p. And why would the 2p be higher in energy than the 2s? It's because of those interactions. So the 2p is higher in energy than the s. And when we go to the third level, we see that we've got s and p and also d. And the p is higher in energy than the s, and the d is higher in energy than the p. But now, just to make things extra confusing, we get some overlap here, and the 3Ds are actually higher in energy than the 4S. I just feel even bad trying to explain this to you. Does this make any sense? Because I wouldn't expect it to, really. We're going to come back to this after the quantum hotel. We'll just talk about Hund's rule. When filling orbitals of equal energy, electrons fill them singly first with parallel spins. Okay, let's get to the hotel. The quantum hotel is a discount resort for electrons, in Mrs. K's Chemistryland. I've mentioned Chemistryland before. So, all of this stuff, I've found this analogy that seems to work because it relates all this craziness to something that you can understand staying in a hotel. So, the floors in the room, the floors in the hotel, it's a multi-story hotel. The floors correspond to the principal energy shell, principal shell. Each of the rooms on the floor are subshells. Each of the beds in the rooms are the orbitals. Electrons are the people, and money equates to energy again, like it so often does. So the first floor of this hotel has one room. It's the 1S room. The second floor has 2 rooms, 2S and 2P. The third floor has 3 rooms, 3S, 3P, and 3D. The fourth one would have 4 rooms, right? 4S, 4P, 4D, 4F. We're not going to get up to F much at all, but it's there. Okay, so you got the idea. As you go up the floors in the hotel, each floor has one more room. It's kind of an unconventional hotel. It's like one of those Vegas-style crazy things. It's like an inverted pyramid. It gets bigger as you go up. So the S rooms each have 1 bed in them. The P rooms have 3 beds. The D rooms have 5 beds, and the F rooms have 7 beds. You're like, okay, this is a little weird. Yeah, it is. And one of the rules here is you can only have 2 people per bed, no sleeping on the floor, and you have to have opposite spins in the beds. So I tend to think of these electrons as being, like macho high school boys, So 2 high school boys on the football team, and they're going to an away game, playoff game or something. They got to stay in a hotel. Are those boys going to be excited about sleeping in the same bed together? Guys? Anybody? My experience, not, being in the room with the guys, but hearing about it afterwards, is that half of them slept on the floor. right? They're not going to sleep in the bed. Well, you can't sleep on the floor here. So this is what they do. So here, oops. So here's a picture of the bed, right? And it's got some sort of a fancy headboard, right? And so the first guy comes in, and he's going to sleep right side up in the bed. The next guy comes in. He maybe doesn't even know this other guy. He has to sleep in bed with him. He's going to sleep upside down. Could you imagine it? It could happen, right? Okay. So this is opposite spins with the electrons. Here, the bed is the orbital. And the first electron is going to go in right side up, because who wouldn't? And the next one that comes in is like, well, I'm not sleeping right next to you. I'm going to go upside down. So we can take this picture here, this diagram, and this is the hotel. Dang it, I keep forgetting. Got to choose a pen. So here's the hotel, right? It's got this crazy shape. Not real stable, but whatever. So here, this is like the elevator going up. And on the first floor, there's one room. It's the S room. It has one bed. Each of these lines represents a bed. Second floor, there's two different rooms. The S room and the P room. This one's down the hall. And the P room has 3 beds. On the third floor, S, P, and D rooms. The D room has 5 beds in it. Just because. The fourth floor has S, P, D. We're just not showing the F because we're not going to go there. Each of these beds could hold 2 people, 2 electrons. Okay? As you go higher in the hotel, the rooms cost more money to stay in. As you go higher in higher shells are higher in energy. So the 4S is higher in energy than the 1S. It costs more money to stay in the 4S room than it does in the 1S room. The electrons are cheap. They're going to stay in the cheapest room possible. So they're going to fill in the cheapest rooms. Now, on the second floor, the P room is more expensive than the S room. Maybe it's further from the ice machine. I don't know. Quieter. It's got 3 beds in it. On the third floor, the P room is more expensive than the S, and the D room is more expensive than the P. But there's this weird thing where the 4S room is actually cheaper than the 3D room. Are you following me on this? It's a little weird. It's not as weird as the other stuff I was telling you. We can imagine this, right? And then the fourth floor also has a P room. That's more expensive than the 3D room. And then there's a 5th floor. The 5S room is next. It's cheaper than the 4D room. So there's this weird overlap here in pricing. But don't hotels have odd pricing schemes sometimes? They do. So we can just be okay with that. And I'm going to show you that all of this is hiding on the periodic table. The order of all this is on the periodic table. So let's go back and do this problem that we missed. So we're supposed to do an electron configuration and an orbital diagram for carbon. Again, I like the orbital diagrams. So carbon has how many electrons? 6 electrons. So we've got 6 electrons coming to the hotel, and they're going to take the cheapest rooms first. So I'm going to kind of sketch this out for you. Here's the first floor. How many rooms on the first floor? 1. And it's called 1S. On the second floor, how many rooms are there? 2. There's the 2S. And then how many beds are in the 2P room? 3. So there's 3 beds over here, 2P. And I'm just drawing it a little higher to remind us that that's higher in energy. It costs more money to stay in. So we don't have to draw out the whole hotel. We just draw out the bottom floors. So now the orbitals, the electrons. The electrons come in here to stay. I'm going to make them red. So the first electron goes to check in. He wants the cheapest room, so he takes the 1S room and he's going to lay down right side up in the bed. Second electron comes in, and he also, there's a spot in that cheap room, he's going to take it, but he's like, well, okay, I'll sleep upside down next to this guy. Third electron comes in, he's going to take the 2s room, because it's the next cheapest. It's the cheapest thing available. Fourth electron comes in, he's going to share this bed and room with that electron, but sleep upside down in the bed. So there's 4 electrons. Electron number 5 comes in. And so this is the cheapest room available, so he's going to go in there, he's going to take the first bed he sees. Now, electron number 6 comes in. This room costs you the same whether you sleep in your own bed or you share a bed with someone. So electron number 6, is he going to sleep upside down with this guy? No, he's going to take his own bed, right? That is Hund's rule. Hund's rule says that the electrons, when they're filling orbitals with the same energy, they'll take an orbital to themselves first before they pair up. Pauli exclusion principle says that you can have 2 electrons, no more, in an orbital, and they have to have opposite spins. So one has to sleep upside down. Any questions about how I did that? Does the hotel thing help? A little bit? This is going to take some practice. Yeah?
So if I had, let's say, 3 more electrons, would it fill one at the end and then that first one again? Or would it fill one at the end?
Yeah, so the next electron would go in here, right side up, and then they'd start filling in upside down. Yeah. So they're going to take their own bed, their own orbital, if they can. But they're not going to pay more just to get that. So they will share if they need to. But they'll sleep upside down. So this is the orbital diagram. The electron configuration I think of as a little bit like the guy at the front desk, and he has to keep track of where the electrons are, so if another one comes in, he can send them to the correct room. So the electron configuration is just a shorthand way, without drawing pictures, that we can indicate where the electrons are. So we're going to start with the lowest energy, which is 1s. So there's the 1s room. How many electrons in it? 2. 1s2. The next room is the 2s room. How many electrons in it? 2. The next room is the 2p room. How many electrons in there? 2. So the superscripts tell how many electrons are in the subshell. So 2p has 3 beds in it, but it's the one room. How many electrons are staying in the 2p room? 2. And this does not say anything about what beds they're sleeping in. It just says how many are in each room. Okay? Any questions? This is one method of remembering the order of filling. I don't recommend it. So you can read about it in the book. If it works for you, great. It's actually all on the periodic table. So this periodic table is color-coded. So we talked about the S subshells. The S room in the hotel has how many beds? It has 1 bed that can hold how many electrons? 2. So you see this section of the periodic table that sticks up, there's 2 columns. Those represent the 2 places in the 1s room. The 2p room, any p room has 3 beds in it and can hold a total of 6 electrons. 3 orbitals, 6 electrons. This pink area here represents the p block, 1, 2, 3, 4, 5, 6. Is that a little spooky? I think so. The D room has how many beds? It goes 1, 3, 5. It's odd numbers. 1, 3, 5. So it's got 5 rooms. It can hold how many electrons? 10. How many columns are here in the orange? 10. Oh. The F room, we've got 1, 3, 5. What's next? 7. So an F room, which is only found in the higher levels of the higher floors of the hotel. The F room can hold 14 electrons. You can count these green ones. There's 14 columns. So what I think is like just crazy amazing about all of this, the shape of the periodic table came about by observing patterns in behavior of different elements before we even knew what an electron was. And they developed this quantum mechanical model based on looking at frequencies of light that are given off when you zap an element with electricity and doing complex math with that information, and we end up with something that mirrors the patterns on the periodic table. That is amazing. Okay, so how do we use the periodic table to predict the order of filling? So the period number corresponds to the principal shell number. So n equals 1, n equals 2, n equals 3, etc. That's the floor of the hotel. On the first floor, there's one room, the S room with 2 beds. Well, here at the bed, those guys, they don't look like they're together, but you could envision that helium could be over here, right? So there's the 2 beds. So helium is going to have 2 electrons, and they're going to be in the 1s. So it'll be 1s2. So that's its electron configuration, 1s2. After that level is filled, then the next electron goes up to the n equals 2 level and goes into the first room, the S room, and we can put 2 electrons in there. So I see this as just counting over. What we're going to do is like with carbon, has 6 electrons. You're just going to look as you go across. So there's the 1 level, 1s2, and here's 2s, 1, 2, and then this is p on the 2 level, 1, 2, and then we get, this one ends with 2p2. And this would be p3, p4, p5, p6. We've filled up the 2p room. We have to go up to the next floor. That's the 3rd floor. We fill up the 3s room with 1, 2 electrons, and then we go to the 3p room, and we put 6 electrons in there. Now, because of this weirdness in pricing, you don't go to the 3D, you go to the 4s room because it's cheaper. And after you fill up the 4s, then you go to the 3D. Now, why is that 3 when it's in period 4? So I kind of think of this as having sunk. So let's get rid of helium over here. This is kind of stair step, right? Down 1, and there's a drop here. So I think of this as like the land in the Central Valley, where our water table is falling and our land is sinking too, right? So Central Valley of California, it sank. So this is a D block, but it's actually the 3D block. So it sank down. So it's the period -1. So then you fill up all the Ds, and you go over here, and now you're into the Ps, 4P, and then 5S, and this is sunken again, 4D, 5P, 6S. After that, things get a little crazier. We're not going to go past barium. Any questions? So summary, lower energy orbitals fill before higher energy orbitals. Cheap rooms fill before expensive rooms in the hotel. Orbitals can hold no more than 2 electrons. Beds can hold no more than 2 people. When 2 electrons occupy the same orbital, they have to have opposite spin. When 2 people sleep in the same bed, they have to sleep head to toe. When orbitals of identical energy are available, all of these are first occupied singly by electrons with parallel spins rather than electrons in pairs. So electrons going into a P room or a D room where there's multiple beds, each person is going to take their own bed and sleep right side up before they pair up and somebody sleeps upside down. So write electron configurations and draw orbital diagrams for nitrogen, oxygen, fluorine, and neon. So we have our periodic table on the wall. Let's do electron configurations first. So I'm going to draw it out first. So here I have the first floor, 1s, and then I've got the second floor. I didn't leave enough room. Oops. 2s. And then there's also there's a 2p. And then next up would be 3s. So those are my rooms. Let's see. Nitrogen. So let's do nitrogen. How many electrons does nitrogen have? 7 electrons. So we've got this pattern here, like a map of the hotel, and we're going to put the electrons in. So 1, the next one has to share, 2, 3, 4, 5. The next one's going to take his own bed, 6, 7. So to write the electron configuration then, we're just going to indicate how many electrons are in each of these rooms. In the 1s, there's 2, 2s, 2, 2p has 3. 1s, 2, 2s, 2, 2p, 3. Any questions? How many electrons does oxygen have? Oxygen has 8 electrons. So as its 8 electrons are going in, they're going to follow the exact same pattern as nitrogen's electrons. The electrons always fill in the same way. So we already have 7. Where's number 8 going to go? It's going to have to share this bed and sleep upside down. So then we can write the electron configuration for oxygen, 1s2, 2s2, 2p4. The superscripts here add up to the total number of electrons. So 2 plus 2 plus 4 is 8, and 2 plus 2 plus 3 is 7. Fluorine. How many electrons does fluorine have? 9 electrons. So where does the 9th electron go? In this second box here is your share. And then the electron configuration, really similar. 1s2, 2s2, this time 2p, 5, because there's 5 electrons in this room. Neon. Neon has to be orange. How many electrons? 10 electrons. Where's the 10th electron go? Right there. 1s2, 2s2, 2p6. The electron configuration of neon represents filling this level. The second floor of the hotel is completely full. Turns out that's kind of a special thing when you completely fill a level like that. Any questions? As you can imagine, if you go on and do larger and larger elements, this could get a little complicated, right? So we have an abbreviation. So let's look at sodium. Well, how many electrons does sodium have? It has 11. So we've got the 1s room, and that can hold 2 electrons. Next up is the 2s room, can hold a maximum of 2 electrons. The 2p room can hold 6 electrons. And now we need to get into the 3rd floor, the 3rd level, and put 1 electron there. So there's the electron configuration for sodium. But this part right here is the electron configuration for neon, right? We just did that. So as a shortcut, we can abbreviate this as the electron configuration for neon and just the extra stuff. So this is the full electron configuration for sodium, and this is the noble gas shorthand. Any questions? Yeah.
Does it have to be the element right before it?
It needs to be the noble gas right before it. Yeah, it's always the noble gas. Because the noble gas represents a complete filling of a valence shell. So let's write electron configurations for each element. You still want the boxes to help you? Or are you okay with just doing the electron configurations? Electron configurations. So the first thing we always have to ask ourselves is how many electrons? 13? Yeah, okay. So 13. So then we imagine the hotel. I picture this in my mind. So on the 1st floor, there's an S room. That can hold, I'll put 2 electrons in there. Go up to the 2nd floor, there's an S room. I'll put 2 electrons in there. And then there's the P room, and I'll put 6 electrons in there. And then I'll go up to the S, the 3rd S, the 3S. I put 2 electrons in there. And so I've got 12 now. And then I need 1 over here. I need a periodic table. I don't have a periodic table. I'll draw an ugly periodic table. Okay, it's pretty ugly, but you get the idea. So, S, P, and D. We're not doing D's right now, so those got really tiny. So, aluminum is, wait a minute. Let me fix that. There's hydrogen. Ah, it's still not good. Okay, this is what I'm going to do. I'm going to go back here because I can't draw today. Of course, I can't draw any day, but that's okay. Okay. So we find aluminum on the periodic table. There it is, right there. Okay? So to write the electron configuration, I look at the periodic table. 1s2, 2s2, 2p6, 3s2, and I'm going to stop here. This is the 3rd row, and this is the p block, and there's only 1. Okay? I think the next one it asked us to do was bromine. So we find bromine on the periodic table. Oh, here's bromine. So this one's going to be a little longer, huh? So bromine, I'll write it up here. We're following the same pattern. We're looking at here, 1s2, and then we come over here, 2s2, and then we're over here. This is 2p6. Next is 3s2, and then we get over here, 3p6. So far, not too bad. And then we come down here, 4s2. And we get to these guys. This is the D block. Remember, it sank down. So this isn't 4D. This is 3D. This is like, there's some special promotion, and so the 4s was cheaper than the 3D. We would expect to go from 3p to 3D, right? But no, there's a deal today, and the 4s room's cheaper, so we're going to take it. So this part represents 3D, and there's 10. And you don't have to remember how many electrons fit in there, because you can count the blocks if you need to. It's 10. And then I come over here, I'm back to 4. This is the 4p, 1, 2, 3, 4, 5. 4p5. Forgot the 10. It's a weird counting game on the periodic table. It's a lot of letters and numbers. That's why there's a shorthand. So let's do the shorthand, the noble gas shorthand. So the way you do that, you find bromine, you go up a row to the end. Argon is the noble gas that is before bromine. We don't want to go all the way back to neon or helium, because then we're going to have to write more stuff. And krypton's really close, but it's further, and you can't do any subtracting. So it's going to start with argon, and then everything that comes after argon. So I'll put that down here. We're going to put argon in brackets. So from argon, we're going to go over here. This is 4s2, 3d10, 4p5. Not 4. 4s2, 3d10, 4p5. So this also represents bromine. Questions?
For master chemistry, which one would it be at?
I think they'll be specific. Anybody have a printout and know what the other one on that slide was? SR? Strontium. Okay. So let's do strontium. So we got to find strontium on the periodic table, and it is down here. You want to do the noble gas shorthand first this time? Yeah. So we're going to go up a row and all the way to the end. Here, the previous noble gas is krypton. So we start with krypton in brackets, and then we go with what comes after. Well, here's 5. This is the S block, and 1, 2, 5s2. So that one's pretty simple. We also have to know how to do the whole thing. And again, I'm just reading it off the periodic table. So 1, this represents the S. Think of helium as being over here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is the D block. It sank down. It's not 4D, it's 3D. 3d10, 4p6, 5s2. Yeah, I forgot something in there. Sorry. 4s2, 3d10, I forgot the 6. I wasn't looking at the periodic table. 4p6, and then 5s2. If you add those superscripts up, they should add up to 38. Doing it this way, you take the number of electrons that krypton has, 36, and add these guys. Any questions? Yes?
Still though, I understand how you did the clarify list too. I still understand how you did it the long way.
Okay. So let's imagine helium over here. So these period numbers are the large numbers here. You okay with that? And this is the S block. So as I'm just going to go across in order of increasing atomic number. Let's get rid of him. So I mentally move helium over so that he fits in there. These, they're little guys and they mess things up. So 1, here's the S block. There's 2 squares, 2, S, 2 squares, and then I have to keep going from 4 to 5, and this is still on the second row of the periodic table. This is the P block. I have to go all the way across. That's P6. And then I come over here. This is 3S2, and I go all the way across here. 3P6. Oops.
That's what I understand how it goes from 2 to 3 on the other side.
Well, this is 3S, and this is 3P.
Oh,
Okay? And then 4S, and this is the part that I would expect people to have some trouble with. Because why isn't that 4? So for these guys, let me get rid of those. We don't need those now. For the D block, you're looking at n minus 1. Right? So the period numbers correspond to n. N equals 1, n equals 2, etc. And so we're here, n equals 4. And that's why this is 4s2. But when we get here, it's 1 less than that. So this is 3d. That's only for this part in the middle, the transition elements, the D block. It's only for the D block. When we get over here, we're back into the main group, and it goes back to 4. 4p6, and we come over here, 5s2. If we needed to continue on, this would be 4d. We go across 4d. This is 5p, 6s, and this would be 5d. And I'll spare you what happens with the F. It's similar, but we don't need to go there. Does that help? So if you learn to read it off the periodic table, it's easy. It's like memorizing a code, learning how to speak Pig Latin or something, and then you've got it, and it's okay. If you try to just remember this, it's going to be tricky, but it's all right there in the periodic table. It takes some practice. Any other questions?